Hey everyone, I'm Asanda, and through these videos we will be going through probability theory from a measure theory perspective. Um, just a few things to note before we begin. This material is based on the lecture notes from from the UCT Stats 3045 course, alternatively known as Order Out of Chaos 2. And these videos are a way for me to sort of like try and understand the material and help anyone out there who may be struggling with the content as well. So I will be making mistakes now and again, forgive me. Just try and point them out, and I'll try and rectify them. So you've probably already encountered the idea of probability from somewhere, maybe high school, maybe some prior course in university. And in that idea or in that course, perhaps what they would have taught you was to calculate probability or how to deal with probability from a relative frequency point of view. So what do I mean by this? What I mean is you have particular experiments. Say you're rolling a die, right? So you have a nice, okay, this does not look very nice, or die, but say you had a nice six-sided die, right? And you wanted to determine the chance of getting, the number 3 from rolling the die. The way that you would approach this problem or this task would be, well, to roll the die, say 1,000,000 times, and then note down the number of times you got 3, and then calculate the relative frequency of getting the number 3, or the relative frequency of the outcome 3. So you'd count the number of times that you would get this particular outcome, right? And then you'd divide that by the number of trials, say 1,000,000, and then this would give you your relative frequency, which would then give you the idea of the probability, right? So we then say that the probability of the event 3 is then this quantity as the denominator tends to infinity. So that is probably the idea of probability that you have, right? So what is the problem with this definition, or with this idea? Well, it's not so much a problem, more so an insufficiency. So there's really a bunch of insufficiencies or problems with this particular idea, but I'll only try to explain one of them. So imagine the very same scenario, but now I tape up all the sides of this die with 6 stickers. So the sticker only tells you, sorry, not 6, yeah, 6 stickers because 6 sides. The sticker only tells you whether the number underneath is odd or even, and whether it's prime or composite. So it only tells you odd or even, prime or composite, right? So we're going to have 4 types of stickers, obviously 6 stickers for 6 sides, but 4 types of stickers in total, because we're going to have 4 combinations, right? We're going to have odd and prime, odd and composite. We're going to have even and prime, and we're going to have even and composite, right? So these are going to be our 4 stickers. So say now I ask you once again to determine the probability of the outcome 3. Right, so now how would you do this? Well, let's say you used the same approach, right? You roll the die 1,000,000 times and you try to note down, well, how many times do I observe the number 3? And you divide that by the number of times you've rolled the die, right? So easy. But not so easy. Why? Because the number 3 will be hidden under the sticker odd and prime, right? So every time you observe the sticker odd and prime, you could say, oh, look, I observed 3. But that's not quite true now, is it? Because the number 5, excuse my bracket skills, the number 5 will also be under the sticker odd and prime. So every time you see odd and prime, the only thing that you can say is that the event given by A, this particular event has occurred, but we cannot say with any certainty whether this or this has occurred, right? So how do we then deal with this? So now we see why this idea that we had previously was perhaps insufficient, right? So in order for us to deal with this effectively, we're going to have to take a bit of a detour into a branch of mathematics known as measure theory. Right. So what is measure theory, and well, what is the purpose? So again, a bit of a disclaimer. The ideas and the explanations that I provide here are not the strict definitions. They're merely me trying to interpret what I read and make sense of it in my mind. So if some of the ideas are wrong or perhaps not accurate, do forgive me. But yeah, this is merely me trying to make sense of the material, not sort of like a rigorous study of the material itself. Okay, so back to the content. So what is measure theory? So in order for us to understand or to try to understand what measure theory could be, or what the goal of measure theory is, I want you to picture a street, right? So say you had a street outside your house, okay? And in the street you had houses. Oof, that's a very skew house. Say you had houses. That's house number 1. That's house number 2. And you had a road. And you had some people walking on the sidewalks. And say you had a car driving down the road. And say you had some piece of trash floating on the side there, right? So this is a street. Now, just this little corner of the universe contains a multitude of information. Now, what do I mean when I say information? Well, let's zoom in for a second, right? So let's consider the trajectory followed by the little piece of trash as it floats in the wind, right? So we're zooming in on this picture and we're trying to focus on this little piece of trash as it flutters in the wind, right? So it's just floating there. So this trajectory is determined by a whole lot of different things. First one of which is wind speed, obviously. So you could even say maybe force of the wind. You could also say perhaps the dimensions of this little piece of paper. You could also say the air resistance it experiences. Right. So all of these things are pieces of information that we can note down. So all of these things and more that we can note down and ultimately use to determine, well, how will this thing fly through the air and eventually get to the ground, right? So again, that is what I mean when I say information. So all of these things can be recorded, all of these things can be calculated, all of these things can then be inputted into some formula that we can then use to find this part over here, right? So going back to my picture, I hope that now makes you appreciate just how much information is contained in this little corner of the universe and ultimately in the entire universe itself, right? So everything happens because of something. Everything happens because of some force. Everything happens because of some event that caused it to happen. The car moves because there's some combustions occurring in its engine, right? And those combustions are calculated, which means they contain a certain level or certain amount of information. And all that information is calculated, it's calibrated, it's measured, it's, you know, it's got meaning. So the whole goal, or part of the goal of measure theory, in my view, is then to find a way to measure information. And in order to do this effectively, we will take that picture of our street and we'll break it up into categories, right? So we'll look at lengths. So the length of the houses, the length of the people, the length of the road, the length of the car, anything that has a length, measurable length, we will put in this space. We can have a space of masses, the mass of the car, the mass of the people, again, the mass of that little piece of paper, the mass of the children, the mass of anything, really, we can put in the space of masses, and so on and so forth, right? But what we're more interested in this course is the space of probability. Now, what do I mean by this? So, with these spaces, lengths and masses, we have physical objects that you can see, but with the probability, it's not probability, okay. But with the probability space, we have something that you can't really see, something that's a bit intangible. So let's go back to the car, right? So let's say you have that car we had back there. We zoom in on it. Okay, so there's my car, and my car reaches an intersection, and say it could take 1,000 different directions, right, from this intersection. Now, before it takes any one path or any one direction, all the paths are possibilities. And in the same sense, all of these paths and their probabilities then comprise the probability space. In the same sense that all the lengths that we saw in our little street gave us the length space. In the same way that all the masses that we could calculate or that we could measure gives us the mass space. So the probability space consists of all outcomes of a random event and their probabilities, right? And it will be our focus, but now and again I will come back, or I will refer to the other spaces to sort of like facilitate understanding of the particular concept that we're dealing with. So with all of that out of the way, I think we're now ready to begin a more rigorous study of measured theory. Right, so we begin our study with a set, a regular set, right? So you will denote the set omega. So this is just going to be a set of objects, any objects that you can think of. So I like to think of this as a universe that comprises of little globs of information. So that information could be infinitesimally small units of length, could be infinitesimally small units of mass, could be probability events, could be anything. So anything that has some measure, idea or notion associated with it, right? So that's our omega, that's the set that we begin with. So from the set omega, we will go on to what we call an algebra. So what is an algebra? Well, an algebra is a subset of the power set. That satisfies three conditions, which we'll now list. But before we list those conditions, let's go to here so that there's no confusion. So this over here is a subset, or is a set of all possible subsets of omega. So we denote the power set by that, that symbol over there. This does not necessarily mean take 2 and take 2 to the power of omega. It's just a symbol that we use to express the idea of all possible subsets of omega. Right. So an algebra will then be a subset of the power set that satisfies the following condition. Number 1, the empty set must be an element of the algebra. Number 2, if A is an element of the algebra, I'll just write alg, then a complement must be an element of the algebra as well. That's condition number 2. Number 3, if A and B are elements of the algebra, then the union of A and B must be an element of the algebra. So those are the conditions that we have in the notes, right? And the third condition, by the way, speaks of all, or speaks to all finite unions, and not just 2 events. So it could be three sets, 4 sets, 5 sets, 6 sets. So, by the way, all these guys, A, B, all these guys have to be subsets of omega. You can't just take any random sets. So they all have to be subsets of omega. So an algebra will be a subset of the power set that satisfies these following conditions, right? The empty set has to be in there. If A is an element of the algebra, then a complement must also be an element of the algebra. If A and B are elements of the algebra, then the union must also be an element of the algebra. And all finite unions of elements in the algebra must also be elements of the algebra. Right, so we further have what we will then call a sigma algebra. Use this little corner over here. A sigma algebra, if we have this fourth condition satisfied, if A1, A2, A3, all the way up to infinity are elements of this algebra, then their union must also be an element of the algebra. So what this fourth condition does is that it takes the third condition that we had over here, which spoke specifically to finite unions, and speaks of, or extends it to infinite unions. So that's all that third condition, or that fourth condition rather, does, right? So what does this mean in I want to say practically, but we are very, very deep in the theoretical view here. But then what does it all mean? What do these conditions imply, right? So if we go back to the idea that we had, right? So we began with this universe, right? That had these floating globs of information. And we call this universe omega, right? So from this universe, we will then have clumps of information, clumps or bags of information. Okay, so I'll use bags. Okay, so imagine those are bags, right? So we have bags of information. What do I mean when I say bags? I mean that you take these globs of information and you take all combinations of them, all possible combinations, and you put them in bags. And these will then be our subsets of omega, right? And you take these bags of information, right, and you put them in a box. What we're saying here is that this box will be a sigma algebra if it satisfies all those conditions that we gave in there. So again, the question is, what does this mean? So remember, we are speaking here, or we are talking here about information, right? So the first condition says the empty set, or the empty bag. The bag with nothing in it has to be in there. So what the sigma algebra is basically a box of those bags that I can measure. So remember, we're trying here to define what measure is, right? Or what measure of information is. So the sigma algebra, in a way, sort of like provides us with the basis to then define measure. Because in most cases, it is almost impossible or impractical to define a measure on omega over there, right? What do I mean by this? Take, for instance, length. If I asked you to give me the smallest unit of length that you could possibly think of, right? Maybe you could say centimeter, but that's not really the smallest, is it? You could take a half of a centimeter. You could take half of a centimeter. You could take a half of that. And you could further take a half of that. And you could continue going. Like, you could literally get to, or, well, you can never get to, but think in your mind, continuously halving the half, until you get to the infinitesimally small unit of length. You can't measure it, right? So if you think of that as this guy over here, then the clumps are the lengths that we can measure, those things that we can see, right? So the length of a table, the length of a ruler, the length of a chair, the length of a person, or the height of a person, right? So all of those are then made up of us adding up all those infinitesimally small units of lengths into clumps. Same thing with events. If you go back to our experiment, well, you can't measure the probability of the event or the outcome 3, but we can measure the probability, or we can attempt to measure the probability of a clump of outcomes. In our case, it was the event 3, 5, right? So this is a clump of the outcomes, a clump of the globs of information, right? So that is our purpose here, and that's what the sigma algebra basically, in my head, means or tells us, right? It gives us a basis to then define what measure of information is. So those conditions that we saw basically help us to create this box of what we will term measurable information, right? So in what sense? Let's bring the conditions back. So let's look at the first condition. The empty set must be an element of the sigma, or the sigma algebra, or the algebra. What does this mean? All this is telling us is that the bag which contains nothing, or the concept of no information, should be measurable. So in order for me to be able to define a measure, in order for a set to be a sigma algebra, or a box of measurable items, then it should have within it the empty bag, or no information, right? It should have the idea or the concept of no information. So for instance, if we go to length, I should be able to define a 0 unit length, right? If I've got, I should be able to assign to something the notion of no length. In the case of mass, I should be able to assign the concept of no length. In the case of probability, I should be able to assign the concept of no outcome to something, right? So if you think back to all those spaces that we looked at, that is what this condition implies, right? So I should be able to give meaning to the motion, or the notion, rather, sorry, of no information provided. The second condition says that if an event, or if a set is part of the algebra or sigma algebra, then its complement must also be part of the sigma algebra. Now, what does this mean? Well, this essentially says that if I know what something is, so if I have information about what something is, then logic dictates that I should also know what it isn't. If I know that something is pink, I should know that it's not blue, it's not green, it's not red, it's not any of the other colors, right? So that's what this over here tells us. It tells us that if I know what something is, I should know what it isn't. I should also have information about what it isn't. And then finally, the last one. So the last one speaks to unions, whether finite or infinite unions. If I have information from certain parts of something, of some space, then putting those parts together should also give me some information. Again, for example, if I have information about an object being green and the object being 5 centimeters long, for instance, then putting those two pieces of information together should also give me a piece of information. So the sentence, the object is green and 5 centimeters long, should also logically give me some information. So all these conditions do is they sort of like provide the basis once again for us to define the measure of information, axiomatically, if you will. So they provide then the foundations or the mold for us to then start and define the measure of information. So in the next video, we will look at then what is a measure, how do we define a measure properly from a mathematical point of view, and what that means intuitively.